of some of selected nearby supermassive black holes. So some of you might already listened part of this talk, as I've been presenting it in some other meetings, and as we started this work around 2 years ago. So, but at the end, I will show some of the new results related to this topic. And we will be speaking about the application of this mechanism, basically the energy extraction mechanism, to the high energy cosmic rays, relativistic jets, or the hotspots around the black holes. Yes, so we start from the fact that any astrophysical black hole is supposed to be rotating, which states so-called Kerr black hole hypothesis, which means that any black hole can be fully characterized by only two parameters, its mass and its spin. We all know about the properties of the Kerr black holes, that it has two horizons, inner and outer horizon, and the ergosphere, which I will be speaking about a little bit later. But what is important, that the total energy of rotating black hole contains from a huge part of the extractable energy. So this is a part of which corresponds to the rotational energy of a black hole, which one can extract basically. So from the black hole mechanics and its correspondence to the thermodynamics, one can derive the extractable energy or irreducible energy of a black hole, because we can introduce the entropy of a black hole, which is proportional to the event horizon area, and from which we can find that up to 29% of the total energy of rotating black hole is hidden inside its rotational energy. Therefore, they can be extracted. And for typical supermassive black hole, this energy is of order of 10 to 74 electron volt, which is tremendous energy, right? And the question arises how to extract this energy in the most efficient way. So another interesting property of the black hole, that it has so-called ergosphere, which is limited from one side by the event horizon, outer event horizon, and from other side by the static limit. And inside this region, you can calculate the time component of the metric tensor, and you may notice that inside this region, it changes its sign, which basically, when we speak about some test particle and its energy with respect to a static observer at infinity, not the energy, proper energy of a particle, but the one which is measured by observer at infinity, it is connected with the time component of metric tensor, which changes its sign inside the ergosphere. Therefore, this energy can become negative inside this region. And this was the first idea which was formulated by Roger Penrose 51 years ago, who proposed interesting and rather simple mechanism how one can use this negative energy to extract the actual energy from the black hole. So the mechanism was the following. So when the neutral particle falls to the ergosphere from infinity, it splits into two parts, and if one of the fragments of the decay or split obtains negative energy, then the second fragment should escape from the black hole with greater energy than the energy of the first particle due to energy conservation law. And we can calculate the efficiency for this process, take into account all the conservation laws and equations of motion. We can find that actually this efficiency, which is defined as the total energy extracted to the total infalling energy, that this efficiency is quite limited with maximum only 21%. Yes, so one can increase the energy only to 21%, which is not sufficient to explain these high energy emission from these AGNs and black holes in general, and relativistic jets and so on. But idea was developed historically during these 50 years, been many proposals of various versions of the Penrose process, and one of the most famous, as we all know, the Blandford-Znaiec mechanism, which uses instead of the discrete particles, it used plasma and magnetic fields, which were later simulated by ideal magnetohydrodynamic simulations, which and some of these simulations have shown even that the efficiency of this process can be up to a few 100%. So basically, one can increase the energy up to a few times, right? And I will show below later that we can achieve the efficiency greater than 10 to 10%, basically. So, black holes, astrophysical black holes, are not only rotating, but also immersed into external magnetic fields as any cosmic object, which can be generated due to various mechanisms, basically due to the motion of plasma around black hole. And there are some characteristic values for magnetic fields around black holes. And for supermassive black holes, this is of order of 10 to 4 Gauss, right? But what is important that this field is weak in a sense that it does not modify the gravity and the metric. Therefore, the metric or the space-time around black hole remains scarce because if you want to modify the space-time metric by magnetic field, you would require 10 to 19 Gauss, which is unrealistically large value. However, even weak magnetic field of order of 10 to 4 Gauss cannot be neglected, as you can estimate the ratio of the Lorentz force to the gravitational force. For a typical supermassive black hole, you obtain these very large values. So basically, when we speak about the motion of particles like electrons, positrons, or even protons or ions, the leading contribution to the dynamics of these individual particles are the electromagnetic forces, right? So, so what happens when you have a rotating black hole immersed into external magnetic field? So this means that first of all, we have to specify the symmetry of the magnetic field. So we assume that magnetic field shares the space-time symmetry. So this means that magnetic field lines aligned along the rotation of a black hole, which is quite a relevant assumption. And in this situation, we have non-zero four-vector potential, non-zero azimuthal component of the four-vector potential. And once we have a rotation, this generates the time component, the covariant time component of the four-vector potential, which is equivalent to the induced electric field, right? So the electric field will be induced. So basically, the horizon of a black hole will feel this electric field. So we'll try to neutralize this electric field by the selective accretion into the black hole. And after the selective accretion completed, which will last very quickly, so one can estimate it, it will be within few seconds, even in case of supermassive black holes. So after the process of selective accretion, after the neutralization of this induced electric field, the black hole accretes net electric charge, basically. And this charge will differ for various configuration, will depend on the configuration of magnetic fields, which can be dipole or uniform or any other kind of any other kind of symmetry. But for example, in case of the uniform magnetic field, which is known as a Wald solution, the black hole will accrete this amount of net charge particles. Yes, so at the end, we arrive with two solutions of Maxwell equations. The first is a technical solution with zero charge when this electric field is generated, and second one when the black hole is accreted, already accretes the net electric charge, which is more physical. So, for example, in case of Sagittarius A star, which is a galactic center supermassive black hole, this charge is of order of 10 to 15 coulombs. So this, which appears that in case of, even though this charge is weak in a sense of gravity, yes, so this is still not Reisen-Nordstrom or Kerr-Newman, because this charge is not sufficient to make any disturbance to the space-time geometry, but the value of this charge is quite huge, which can affect to the acceleration mechanisms. So you might ask where the other particles with opposite sign of charge gone. So in this situation, we arrive to the case when black hole accretes net electric charge, and this charge should be equal with the opposite sign to the charge of the magnetosphere surrounding the black hole. So there will be kind of equilibrium between the black hole and the accretion disk or magnetosphere, as you like. And one can actually even test the presence of charge inside the magnetosphere, for example, using the flares, which were recently detected by the gravity experiment in the galactic center. So they detected the flare motion, which around the center of our galaxy at some close distance to the black hole, so the distance of the innermost stable circular orbit with some certain periods. So we can, so if the magnetosphere has charge, then this flare component should be also charged, which would lead to the interaction of these charges with the gravity, and one need to take into account the electromagnetic interactions, which may sufficiently influence to the dynamics of this flare. Yes, and if we estimate, so we can basically constrain, since we know the position and the period of these flares, we can constrain the charge, since we also know the magnetic field values. And it appears that the ratio of the charged particles in the plasma to the number of neutral particles is of order of 10 to minus 8, which means that basically only 10 particles per million particles inside plasma should be to billion pairs of protons, electrons, we have one extra proton or electron. Yes, so from this point of view, plasma still remains quasi-neutral. Okay, so now we can consider having all this knowledge about the rotation magnetic field charges. We can recalculate the Penrose process for charged particles and write all the integrals of motion, conservation laws, and calculate the efficiency of this mechanism, and we arrive with some equation, but which will have three various limits depending on the composition, but depending on whether these particles are charged or neutral. So when all the particles are neutral, we arrive with a Penrose limit, as I already explained, with the maximum efficiency only 21%. When all the particles are charged, as in case of ordinary plasma, yes, then we arrive with some equation for the efficiency of the energy extraction, which will be given as the ratio of the total charge accreted to the total infalling charge. And obviously, this ratio cannot be very large because you cannot sufficiently separate the charges in such a way that you obtain so huge amount of the charge ratios of escaping and infalling particles. But on the other hand, so basically this might be the reason why the blend, so this is kind of Blandford-Znaik limit from one sense, so this might be the reason why you cannot observe very high efficiency in the ideal MHDs. But on the other hand, there is an ultra-efficient regime of this same process when you have a neutral particle which splits into two parts close to black hole, and these fragments are charged. Then with neutral particle, we can come as close as we want to the charged black hole, or the black hole with accreted net charge. And when the particle splits into two parts, two charged fragments, these fragments immediately start to interact. So in addition to the gravitational contributions, they obtain also Coulombic contribution, which accelerates these particles. Yes. So this situation you cannot achieve when you have initial particle charge. So therefore, in this regime, you may obtain the ultra efficiency even for very weak magnetic fields, and you can calculate in more realistic situation. For example, you have a helium atom with one electron lost, and which loses a second electron, and in this situation the efficiency will be only of order of 1, so you can increase the energy to 2 times. But if you consider the emission of alpha particle from neutral helium, which splits to alpha particle with and 2 electrons. In this situation, this alpha particle obtains very high energy with efficiency greater than 1000. But this is the case of the stellar mass black holes with a magnetic field of order of 10 to 4 Gauss. And it is interesting to look what will happen in case of supermassive black holes. So, and for supermassive black holes, we can consider various processes, but various processes of decay. And for simplicity, we can consider neutron beta decays, where we have a freely falling neutron splitting into or decaying into proton, electron, and antineutrino. And if we calculate the energy of proton escaping in this mechanism, you can see that maybe in this equation, yes, that for typical supermassive black hole of magnetic field of 10 to 4 Gauss and supermassive black hole of the mass of 10 to 9 or billion solar masses, the energy of escaping proton is greater than 10 to 20 electron volt. Yes, so energy of free neutron is of order of 10 to 9. So also what is important is the dependence of the energy of proton from on spin of a black hole, and we can see that the difference between the rapidly rotating black holes and say moderately rotating black holes are not so large. Therefore, it is not so much important for this process to have a black hole which is rapidly rotating. Rather, it is important that the black hole rotates. Right? Okay, so the direct application of this mechanism is the explanation of the highest energy cosmic rays. So these are the charged particles with mysterious origin. We know that these are charged particles and they're probably extragalactic. And the maximum energy which were detected so far is of order of 10 to 21 electron volts. So we can see that typical supermassive black hole is already able to provide the energies of the similar orders of magnitude of the cosmic rays with the highest energy. Yes, and even more precisely, so we can look to the best known supermassive black hole candidate. This is a Sagittarius A star in the center of our galaxy, which has a mass of order of 4 million solar masses. We don't know its spin, but we know that it's more likely rotating with a spin greater than 0.5. And magnetic fields are also estimated. And if we calculate the same mechanism for protons, we obtain the energy of protons of the order of 5 to 10 to 15 electron volts, which makes this supermassive black hole in the center of our galaxy, or our galactic center, as very good potential pevatron. Yes? And this pevatron is important also in the case of ultra-high energy cosmic rays. So if you look to the spectrum, you see that there is a knee at the energy of exactly at this energy level, where the flux of the cosmic rays is decreasing when the energy reaches the 10 to 15.5 electron volts, which might be kind of alternative explanation or of the knee of the cosmic ray spectrum. There's a standard one, standard explanation of the knee is the supernova explosions, but in comparison with supernova explosions, here we have a constant mechanism which can provide, so this is not catastrophic event, which can provide the cosmic rays constantly for a very long time. We can also constrain the magnetic fields and masses for various black hole candidates. Here you can see that there are some very nice candidates which could be accelerate the particles to certain energies. So I don't have much time, so I will skip some of my slides. So here we selected 25 nearby supermassive black holes within the distance of 100 megaparsec, because at larger distances, the protons or basically any charged particle with high energy is not able to reach the Earth with such energy, because it will interact with cosmic microwave background photons. Therefore, we have to seek for the candidates. At least in case of protons, we have to seek the candidates for the ultra-high energy cosmic rays within the distance of 100 megaparsec. So here you can see the distances, here the masses of black holes, magnetic fields, which are estimated based on different models. And here we provide the mean values of different estimates. And here we have some estimates on the spin, but for spin, as I already told, in this mechanism is not so important, but rather it is important that they are rotating, and as we can see, most of these black hole candidates are rotating pretty fast. And at the end, we can find the energy of in case of protons. So basically, we can find also the energy in case of if you want to obtain some other composition of the particles for various ions. So in case of protons, we have these energies. So what is interesting in this table, that if we look again back to the spectrum, so we can see that the spectrum shows not only knee and second knee, but also ankle. So its energies starting from 10 to 18.5, there is a flattening of the spectrum, especially in those observed by these Japanese detectors, Akeno, but also Pierre Auger and Fly Eyes observatories also confirmed the existence of this ankle at these energies, which might indicate the presence of multiple sources of these energies. And in this situation, if we look to the energies obtained within our model, then of course we shouldn't look to the Sagittarius A star because it's in our galaxy, but for extragalactic sources, we see that the energy order of magnitudes of energies are relatively close to each other, even though the masses differ almost 3 orders of, or even more than 3 orders of magnitude in some cases. But we see that the energies of protons escaping from supermassive black holes located in different parts of our galaxy, in different parts of the local universe with various masses, which gives similar orders of magnitude for energies of protons. Yes, so
yes, you have 1 minute.
Okay, so this mechanism can also be applied for the explanation of jets, because the particles, the ionized particle, escape along the symmetry axis in a very narrow cone with very large velocities. And so I will skip everything. So, well, I can probably, maybe I can also tell something about some new mechanism, which or make the advertisement of the talk by Martin Kolosh on Wednesday. He will be speaking about the another variation of this energy extraction mechanism, when you can basically, by a single particle radiating inside the ergosphere, you can achieve the very high energies. So this talk will be on Wednesday. So this kind of complementary talk. Yeah. Thank you very much.
So thank you, Arman, for a very nice presentation. And are there any questions? If you have question, just raise hand. I think that there are no questions. So